Hi everyone, I'm back with another circuit question. This is again another good example if you're taking a circuit course in second year electrical engineering or mechatronic. You're a mechanical engineer who took a mechatronic course, or you want to take your PNG exam certificate, and then you have to do a technical exam in electrical engineering, and you chose circuit as one of your technical exams. Okay, so let's dive into it. This is figure 3. Well, it says figure 3. The switch was initially closed for a long time. What does that tell you? Okay, this is very, very important. Then it asks about the initial value of the capacitor voltage, and then the initial kind of current of the capacitor after the switch is turning on, and then at the end what is the voltage basically at infinite time. And then the second part, you can see that this exam has this is 20 points. Okay, it has 20 points, and this is such an easy one to solve. Okay, so we can, if you see this question in your exam, definitely start with it because it's not a very long one. Okay, so first we have to take show the circuit with the assumption that the switch was closed for a long time. What would happen when the switch is closed? This circuit is closed, right? So you can see that. Let's just forget about the capacitor. When the switch is closed, this voltage starts providing current to here, and then the current goes here and then goes here, right? And the current that goes through the 2 ohm and the capacitor starts charging it, right? Right after it starts charging it, when the switch starts, let's imagine that we are at like the beginning of the world, and then the switch is turning on and nothing was on before, and then the capacitor starts charging. Then after a long time, the capacitor is fully charged. When it is fully charged, it can't charge no more. Then what happens? Then the capacitor is like, I'm done, I'm full, don't let any current through me. So that means that the capacitor after t is going to infinity, right? After a long time, the capacitor C becomes fully charged. When that happens, it's and it holds a voltage across its plates, then it says I can't have any current going through me. So no more current through the capacitor. And that kind of forces that branch to becomes like an open circuit, right? Because when this becomes open, this branch disappears, basically, right? So now we want to know exactly what is the voltage of this capacitor after a long time, okay? So we need to know when the capacitor was fully charged, what was the voltage across it, okay? So we have 25 volt here. We have to draw this is right at the time the capacitor was fully charged and the switch is still on, it hasn't opened yet. When it says find VC at time 0 plus, it means that the capacitor was fully charged. You are just turning the switch on, but you haven't done that yet. So So the voltage across the capacitor has to be continuous. It can't jump. So VC is exactly equal to VC at 0 minus, meaning that right before the switch was opened. So that's why we are using the continuity of the voltage to draw this. So when this is open, the voltage across the capacitor is basically, because this has no current, VC 0 plus is exactly the V across the 3 ohm, right? Because no current is going through here. So this 2 ohm experiences no voltage difference across it. So VC 0 is going to be exactly equal to V of the 3 ohm. And now, if I draw that again, simplifying that, this is our 5 ohm, and this is basically our VC plus and minus. Because no current goes through the 2 ohm, because the capacitor forced it, and it's like it's not there. So that's why. And then this becomes a simple voltage divider, 3 ohm over 5 ohm plus 3, because the 5 and the 3 are in series, multiplied by 25. So that's 3 multiplied by 25 over 8. Okay, let's see. Let me write this better and then see if this would get solved for our math. Okay, whatever, yeah. It's 9.375. 9.3. 9 point. So our VC 0 plus is going to be 9.375 or 9.4 volt. Okay? Now, then when we have this one, right? Now that the signal opens, now we have to go back to the equivalent circuit when the switch opens. When the switch opens, this is when switch is closed after a long time, right? When switch opens, what happens? We don't have the 25 volt anymore, actually, because its switch got opened, so it becomes irrelevant. We have the 2 ohm, we have the capacitor, then we have the 3 ohm. VC, okay? So now the capacitor starts discharging. So the capacitor, which had about 9.4 volt, the capacitor starts discharging its stored 9.4 volt. At what rate? Now we have to VCT is equal to VC 0 plus then E minus T over RC. Now, because 3 ohm and 2 ohm, both of them are in the circuit with the capacitor, this R here is going to be 2 ohm plus 3 ohm is 5 ohm. Our capacitor value is half a farad. So then our VCT becomes 9.4 volt E minus T over 2.5. Or we can say 9.4 volt minus 0.4 T. So we answered another question, part 2, for this. Right away, when we have our initial value, which this one was, and we know that the equivalent resistor, the RC circuit, then we can write this. Now let's find what else we are asked. VC at 0. Okay. VC at infinite time, again, okay, let's write this. dVct at time 0. Okay, that's going to be, let's take a derivative 9.4 minus t 0.25, and that's going to be 9.4 minus 1 over 25 e minus t 2.5. At t equal to 0, this becomes, sorry, let me just write this as t, and then dvc dt at time 0 is becoming 9.4 over 2.5 minus. And let's see if this gets solved. Minus 3.76. Okay, minus 3.76 amp. It's kind of in amp, but let's not write it. Okay, then it asks for IC. This is the second part. IC 0 plus. IC is actually C dVc dt. So we just need to multiply what we got before. This is our another question we solved, multiplied by minus 3.76. Again, this is direction, right? The minus only implies the direction. You can remove it, but that is going to be 1.5, 1.8, 88 or something like that. Okay, amp. So that's another one we solved. Then we go to VC infinity. So when 9.4 e minus 0.4 t goes to infinity, obviously, one way is to solve this mathematically and say like an exponential goes to, this is an exponential value. It starts from 1 e to the minus 0.4 t, and then it goes closer to 0. This is 0. You can solve this mathematically and say this is going to be 0. Or you can say intuitively that, okay, and finally, after the switch is on, you know, this is my equivalent circuit here. This is my equivalent circuit. The capacitor is going to be fully discharged. And then by fully discharged, that means that there no longer going to be any voltage across it. What did I do here? VC. Okay, so you can, there are two ways to know what it would be. Yeah, if the switch stays on, the voltage has to get fully discharged, and then that's how you know that the voltage is going to be 0. That's why sometimes when you turn off a circuit, they're like, okay, before you turn it on, actually wait a couple of seconds for the capacitors to discharge completely, and then you turn it back on and they start working properly. Otherwise, no. Also, that's when sometimes you have to short circuit some of the capacitors to fully discharge. Otherwise, they're going to hold some voltage across them, right? Or you have to be careful not to shock yourself with the capacitors by short circuiting them again, because they will discharge across your body, basically. So, okay, that was, I hope this question was also helpful and you learned something. See you next time.